Good morning, dear students. Welcome to another session of DSP architecture and algorithm. In present discussion, we'll be going ahead with some of the architectures which are present in DSP. That is the previous architecture, say instruments from Texas, then Motorola, then we have analog devices. So based on the comparison between them, and then we'll go in depth related to TMS architectures, that is the Texas Instruments for DSP devices. And then we'll be discussing regarding a few instructions, then what is the architecture related to those TMS specifically, what all things are present, say for example, ALU, then address generation unit, then say the barrel shifter, all these things, and say MAC unit. So those all things again will be coming around, but little bit more in depth. So it is previously we had dealt with the overview, that is a skeleton kind of thing, and now what we'll be doing is we'll be filling up that skeleton with the rest of the part. So that is what we'll be doing in this case. Then apart from that, we'll be discussing more in detail about the addressing modes. So previously we had discussed in short that what are the different addressing modes, that is direct, indirect, register. So these all things, offset addressing. So these all things we had discussed. So now we'll be discussing pertaining to the the instructions. So how do I utilize those things and then go ahead? So using those instructions, few programs also will be looking out. So if you understand how logically the implementation goes around, then writing the program is not a big task, because logical implementation itself will be jotted down into the instructions. So that is what we'll be that is what we'll be doing in the coming forth discussions. So in this one, programmable DSP processors. So before proceeding, so we had discussed n number of factors which actually separates digital signal processors from your, say, other processors. Say for example, just the microprocessor or microcontrollers. So if we just see the previous discussions, right, we came across something as, say, for example, we discussed regarding barrel shifter. So what is the advantage of barrel shifter? So advantage of barrel shifters are is that in just one instruction cycle or in just one machine cycle, for example, I'll be able to perform n number of shifts. Whereas in your say a microprocessors or controllers, if you require n number of shifts in a data, then you might require around say n or more than n machine cycles to, or more than one cycle to perform that. Say instruction cycle, I'll specify, not machine cycle. I'll specify it as instruction cycle. So in one instruction cycle, I'm able to perform the shift operation in say digital signal processor. But when we go for microprocessor, this is not possible, because they don't have that kind of hardware architecture. So for example, the barrel shifter is not present over there. So that you have to do with whatever available hardware is there, and then go ahead. So it will take, say, if n number of bits have to be shifted, then in your microprocessor, it might take more than n instruction cycles, depending on, or more than one single instruction cycle. It will take more than one single instruction cycle to complete those n shifts. Whereas in DSP, just in one shift, I can finish off. That is, in one instruction cycle, I can finish it off. Then apart from that, we had discussed that majority of the DSP processors will be having the Harvard architecture. So what is meant by Harvard architecture? In Harvard architecture, you will be having separate memory for program and separate memory for bus. So data. So in this case, what happens? And there will be separate bus accesses for both program bus and data bus. So when we have these things, what happens? I can access at the same time. I can go and access an instruction, and I can go and access a data. So both I can do. Both I can do over there. So if program memory, data memory itself is again divided. Say I have say three data memories, for example. If I specify, suppose I have one program memory, or which is related to program other thing. Then I have data memory. Say I have three data memory. So three data memories and one program memory. So each is having, say, its own bus for its access. So when you're, say, adding two numbers, for example, if I add two numbers, I require two operands. I require two operands, and the result will be stored in, say, in accumulator, what we discussed. Say it will be stored in some another operand. So this is how it goes around. So now here you can see that this is a instruction, so which is related to the program. So I have to go and see what is present in that instruction, which will be stored in the program memory. So add a comma b will be stored in the program memory. So now in add a comma b, what is there? We have two operands, that is a and b. So I have to access these operands. So what I can do is, so I got to know that I have to add two numbers. I know that there are operands which will be present after this instruction. So I can get access to the address, and then I can go and access the operands from different locations. So a might be stored here and b might be somewhere here. So I can go and fetch two instructions, sorry, two operands at the same time. So what I'm doing, I am doing three operations at the same time. I am fetching the instruction from the program memory. At the same time, I'm fetching the operands from the same memory. Now, what happens is you'll be adding the two numbers and we'll be getting the result. So that result will be storing in some other location, for example. So in that case, what happens is you have fetched the instruction, you have taken the operands. So next you can perform the operation because you have the availability of the operands. So this result has to be stored. So that result can be stored parallelly in the other memory location. So here what is happening is you are fetching the instruction, you are fetching the instruction, then you are fetching the operands, and then you are storing the result. So all three operations you are doing at the same time. So in one instruction cycle, you are able to perform this operation. So that is the advantage of Harvard architecture. In one go only, you can do all these things. So it depends on how the memory is being provided. But one separate for program and one separate for data will be there. Data memory and program memory will be separate. At least one will be there. So again, it depends on whether you want one, two. So the depends on the architecture. So this is how it actually increases the speed of execution in DSP. So say with respect to Harvard architecture. Then with respect to barrel shifter also we discussed. Then we had the multiplier. So which was say the Brown multiplier. So in that we had seen 4-bit by 4-bit multiplier. So in this also we can go ahead with just one instruction cycle. I'll be able to get the result of say 4 by 4-bit answer or any number of bits. So in your TMS architecture, right, we'll be able to see 17-bit by 17-bit multiplication, which makes use of such kind of multipliers in which only one instruction cycle is sufficient to execute and get the result of that multiplication. So these are just a few things. Then apart from that, we had discussed the memory aspect, that is whether on-chip is good or off-chip is good. If on-chip is there, how we have to deal with what happens when on-chip memory is there. So it is like on-chip memory implies that you'll be able to access the information at a very faster rate as compared to when you're accessing the information when it is on off-chip. So therefore, you go for on-chip memory, but along with that, you can also interface your off-chip memory so that you can extend that memory. So even those facilities are present. So these are all present in your DSP processors. It is present in these processors. So then apart from this, uh, what happens is many of the DSP processors have a very powerful instruction set. So in your previous listing, you might have seen that you write just add a comma b, then say if you want to loop in, if you want to add the two numbers say 10 times. So what you have to do is you have to write jump, say decrement count. So jump no zero something in this form you write, and you keep on executing that instruction. But those kind of operations can be done in can be done in just one go in using just one instruction cycle in DSP. So that is the power of the instruction set which is present in DSP processors. So this is how it goes around. Okay. So these are just few things to name up. That is with respect to the programmable DSPs. So all the things what we have discussed previously, right? So those all will be handy over here, and those all are the advantages of DSP processors. Okay. So this is what I wanted to discuss. So here in this part, right, we'll be discussing a few devices which are related to the DSPs. Then that is here we'll be discussing regarding Texas analog DSPs and another one from Motorola. So we'll be having a comparative analysis. Then we'll be going in depth the detail of the architecture of this specific DSP processor, which is from TMS, that is Texas, which is 54XX series. So this is again from previous version. There will be some added components or added features with respect to these new devices. So then we'll be discussing regarding the different addressing modes and what are the instructions which are present over there. Then we go ahead with the memory space which is present. So how that on-chip, off-chip memory is presented, how we can go and access it. So those kind of things. So how we deal with the program control. So we had discussed slightly regarding program control aspects. So then in-depth analysis of the different instructions and how we can go ahead with using these instructions to say build say FIR filter or implement convolutional encoder or perform convolution and deconvolution, circular, linear, so everything. So we'll be trying to deal with these things and what are the peripherals using the on-chip this thing. Then how interrupts will be handled, what is the way we have to look out for how the interrupt mask register, how the interrupt flag registers will be utilized, and then what is meant by pipelining. So this is also one specific this thing what we had discussed, that is pipelining actually increases the speed of the execution. So these all things we'll be discussing in this part. So now coming down to the first one, that is the commercial DSPs. So as I discussed previously, all the same, this discussion will be coming over here. So all the commercial DSPs will be having the Harvard architecture. In general, I'll not specify as commercial, all the DSP processors will have the Harvard architecture. Then they'll be having, say, on-chip memories available. Then they can have the barrel shifters which are present. Then apart from that, they can have the multipliers which give the result in, let's say, just a single instruction cycle. Then apart from that, they can have powerful instruction set. So each of them might be having slight different instructions. A few of them might be having say 100 instructions, and few of them might be having 1,000 instructions. That is the instructions for programming. So it depends again how it is, how it goes around. So those are just a few things. And when we speak of these DSP rights, they find their application in not only one, there will be multiple. So presently you can see that it is also being utilized in your artificial intelligence. So if you go back also, you can see that in simple things also it can be utilized, say for speech processing, then for just communication aspects or denoising. So all those things we can deal with the DSP processors. So few they have specified here, that is communication, control, computers, so whatnot. So everything we can just have a look over here. So these are just a few things what I just wanted to specify. So here we can see that Harvard architecture, then a single cycle hardware multiplier, that is say the Braun multiplier, what we had discussed. Then apart from that, we can have different multipliers also, which may be performing much better than the Braun multiplier. So those are also present. So address generation unit. So this is important because we had seen that in DSP, right, we require two special addressing modes. That is, one is bit addressing mode and another one is the circular addressing mode. So if you're performing circular convolution, you have to access the data in a circular form. So that is where address generation unit has to take care how the operands are being accessed. And bit reversed, we had checked out that how we access the bit reversed operation. So we add half the size of the entire unit, and then we go ahead with the accessing the addresses of the data. So that is how we had looked out for. So then again, we have some on-chip memories which are present. Then with say expansion which can be provided. Then apart from that, we can have looping which will be actually presented from the hardware support. Okay. So these are just a few things to name around. Then under this, we can see that few devices which are there, which are from Texas Instruments, Motorola, and analog devices. So these are just a few to name around. Again, there are a number of components under or DSP processes under these itself. So you can see that at the initial stage, TMS 32010 was developed. which was your first commercial programmable DSP. Then later advancements was put over in this one with some few added say features. So in 2020 and later TMS 320C25 was developed, and now we can see that we have 54XX series and different series from the Texas. So which are providing different kinds of features which find their applications not only in your simple communication aspects but also in AI aspects, artificial intelligence aspects. So these are different features which are presented over there, and this is how it goes around. So in again in Motorola they had 56,000, that is DSP 56,000, just a name which is present over there. Then analog devices. Then in that we had EDSP 2100. Now there are again a number of not only from Texas, we can have from different this thing also presented for the DSP processors. So these are just a few to name around. So these all form the commercial DSP this thing, and the major person who is into DSP is your Texas Instruments. So he's the major person who looks after these things. But apart from that, Motorola and other devices also, other competitors also fall in. So this is how it goes around. So there is actually a comparison provided over here. So I'll come to that comparison later. So I'll just show what all things he has presented. So he has presented what is the hardware multiplier, how much bits it is, then what is the ALU. So these all things, what I'll do is I'll not come at present this thing. So what we'll do is we'll have a discussion regarding one of the architectures, and then we'll come back to this, and then we'll have the comparison. So this is one of the important this thing you can just note it down, because comparative analysis is seeked out many times. So you'll have a go through this at a later point of time. So and in diagrams itself, right, what he has given is he has given the architectures on specific processes. So this is TMS 320C25. So at initial go, it is difficult to identify what is what. So as we go ahead, right, we'll discuss one of these processes. Then we'll get to know that okay, few of the things what is actually happening around. So at present, it becomes difficult for you to go around and analyze what is present in these things. So here you can see that you have program bus, you have data bus, and it is accessing some registers, some memories, some multipliers present, shifter is present, some T register, that is temporary registers are present, and accumulators are there. So many things are there. So what we'll do is at starting, we'll not discuss these things. We'll go directly and we'll discuss one of the architectures and come back and see what are these things implied. Say here he is specifying it as shifter. Shifter is actually a barrel shifter, which is present over here, wherein you will be able to shift from 0 to 7 bits. So this is how we have to read this. Then you have here accumulator and see the redundant bits which can be coming forth, that can be put in some other registers, which in majority of the terms it is termed as temporary registers. So then these are the things. So here you can see that ALU is 32 bit. So all these things, so there's a multiplier and accumulator kind of thing. Then why shifters are required for scaling purpose. If you remember, for scaling, whether it is the integer number or whether it is a decimal representation, that is fractional representation. So when you're adding two numbers with different exponents, first you have to make the exponents same, and then you have to add. So those all things also come into play over here. So these are the aspects what we have to look out for. So this is the architecture of the entire PMS 320C25. So just have a look at this. So we'll come and see what all things are present here, what is happening. So just a brief discussion we can have. Okay. So here, this is the architecture which is pertaining to the Texas Instrument. Then in this case, he has given the architecture which is related to the Motorola DSP. So here again, you can see that you have so many things which are present over here: program address generation, program decode controller, data ALU. So here you can see that again, data ALU, program ALU. So those all things are present. You have X memory, Y memory, program, peripherals, so address generation unit. So those all things are present. Then you can see that you have say ports which are provided for communication with the external peripherals. Then so these are just a few things which are displayed over here. Again, apart from this, you can see that you have the buses. So you can see that there are four buses which are present over here. So this is just a representation of your DSP 56,000 signal processor. Then apart from this, the other one, which is from the analog devices, ADSP 2100. So again, you can see that you have arithmetic units, serial ports, timers, then interfaces. So you can see here we have program address, memory address, data memory address, program memory data, and data memory data. So here you can see that there are different buses which are present. Then here you can see that there is a data address generation unit, and even we can have a program address generation unit. That is, I want to go and fetch the instruction at what location it is, then that will be identified by the program address generation generator. And similarly, at what location the data is present, that can be accessed via the data address generator. So such kind of things are present over here. Program sequencer also we had actually discussed in one of the parts. So how do you go ahead with the execution of that program? So those all things will be controlled in this part. So this is just an overview of the analog devices ADSP 2100. So comparison will come after we discuss regarding the architecture. So this is related to the commercial digital signal processors. So now coming down to the data addressing the modes. Sorry, one second. So we'll be discussing regarding the data addressing modes, and we'll be discussing regarding few of the architectures which are pertaining to TMS 320C54XX, which is the TMS device for the DSP, that is digital signal processor. So as again discussed, the repetition comes over here. That is, it will be having the Harvard architecture, which pertains to that. It will be having one separate memory for program and one separate memory for data. So compulsorily that has to be there. But in your TMS 5466, what we have one program memory and you have three data memory spaces. So totally you have four different spaces, one for specifically for program and three for data. So if this is the case, what happens is you can at a single instruction cycle, in one instruction cycle itself, you can access the instruction from the program memory and the two operands on which the instruction has to be executed. Say add a comma b, a and b can be fetched at the same time. And at the same time, what I can do is when I get the result in the same instruction cycle itself, I can go and store the result in the third memory. So this is how the architecture goes around for TMS 320C54XX. So it is having one program memory and three data memory spaces. In one instruction cycle itself, I'll be able to fetch the instruction, the two operands on which I'll be performing the operation, and then I'll be storing the result. So wherein I'll be writing it. So here you can, another thing to identify is you'll be reading from the program memory, and from the two data memory locations, you'll be reading the data. And from the third one, what you'll be doing is you'll be going and writing the information. So two out of three data memory spaces, two are intended for reading from the location from the memory, and one is intended for writing. So that is what you will be performing over in these kind of architecture. So apart from this, again, as discussed, we have the on-chip memory. Again, in that we can have ROM, RAM with single access and multiple access. So these all things. And apart from this, what happens is we'll be able to exchange the information or fetch the data from these memories and have the transfer between them. So this is what we can do in these all cases. Then apart from that, we have the ALU architecture, which will be comprising of the MAC unit, which will be comprising of the accumulators, which will be comprising of, say, the address generation unit. So all those things. So all those will be added over here. So this is just a few things what we are naming around. So here we have the central processing unit. So in this case, right, here. So here we have. So we can see over here So there are so many things which are specified over here. So before coming to this, just so here just a brief of what that CPU consists of. So the central processing unit of 54XX processor, it consists of 40-bit ALU. So what does 40-bit infer is it mentions that it will be performing operation on 40-bit of data. That is how it goes around. So another thing you can just see here is you have actually two 40-bit accumulators. So in your microprocessors, you have seen that you have only one accumulator for performing these operations. But in this one, you have two accumulators. Then you come across with the barrel shifter, which is present in this. You have a multiplier. So in this case, it is a 17 by 17-bit multiplier. 17 by 17-bit multiplier, which provides the result of, say, multiplication in one instruction cycle, or if you have a MAC unit associated with it, then it can perform in a one instruction cycle the multiply and accumulate operation. Then apart from that, you have adder, which is around 40-bit. You have data address generation, DAGen, and then you have program address generation, PAGen. So please remember these short forms because it will be coming around in many of the diagrams, and in short they'll be using these terms. So data address generation, program address generation, ALU, CPU. So the other this thing are familiar with you because already you have utilized those things. But DAGen, PAGen, PAB. So these all or DAB. So these all things are new. So please make a note of these things and then go ahead. So there are again different registers which are present and different instruction set which is powerful enough in 54XX. So those all things are present in these cases. Suppose if you want to loop in, so I can loop in using the instruction set, but loop in is helped around with the specialized hardware architecture. So which actually increases the speed of execution. So that is what happens in this case. So this is what I was specifying, powerful instruction set, hardware supported single instruction repeat and block repeat operations. So for example, if I have a certain set of block, say, say I have a certain set of block and there are n numbers over here. And I want to move these n numbers to some other location, all the n numbers. So if you perform it in your microprocessor, right, what will happen is one at a time will be performing. One at a time will be performing. But using the powerful instruction set of DSP, right, what you have a facility of moving this entire block in one instruction cycle itself to the other location. So such kind of operations, that is block repeat or whatever is there, repeat operations. So those all things can be performed over here. So then that is what block memory move instructions is specified for. Then apart from that, you have several IO ports which act as the peripherals for these things. So you have hardware timer, then wait state generator. We had discussed regarding this, why wait states have to be present. So if I have to recollect it, what happens is, suppose there are two devices which are communicating with each other. One device is fast enough, one device is slow compared with the other one. So suppose you have sent some information and you want to fetch the information from that device. So you are processing data at a faster rate, but the other person might be, or the other device might be processing it at a very slower rate. So you have to wait till all the data is sent back to the data which has been requested. So here, what happens is in such kind of things, say I have the faster one and I have a slower device. So this person has has asked for some information, and this person what he does is he gives this information to the faster device. Now what happens is this information will be coming very slowly, whereas this one will be at a very faster rate. He has got this, but he'll be giving it slowly. So here what happens is he has to wait for some amount of time till all the data what he has requested has to be received. So in that case, what he has to do is he has to go in the wait state. So this is where your wait instructions come into play. You have to put wait states depending on how the other device is. If he is slow, then you have to adhere to his speed. This is just an example what I am specifying. So this is where the wait state generator comes into play, then wait instructions come into play. So then you have the IO ports which can be acting in serial and parallel mode. So these are just a few things to specify with respect to the entire architecture related to your TMS 54XX. So that is this one, 320C54XX. So this is what your 54XX DSP processor includes. So in detail, again, we'll be discussing regarding the bus architecture and the multiplier and other steps in coming forth session.